Hi everyone. We're going to start our new series of videos which is to do with Unit 3 Area of Study 2, and this is all to do with basically how we generate and transmit electricity on large scales. This first part is just going to be looking at how we generate electricity. So here's our key knowledge points from the study design. I'm not going to introduce them every time we start a new video because it's quite a compact area of study. It's not too crazy. There's not a lot going on. So there's actually not that many dot points that we actually have to cover. In particular, there are 3 main dot points that we're going to cover when we're generating electricity. That's the first one here to do with magnetic flux. The second one here where we use basically Faraday's law. And the third over here is describe how a generator works. Okay, these are the 3 main dot points for this particular part of this area of study. So I'm not going to introduce them every time we do a video. This is just straight from your study design anyway. Okay, so without further ado, let's get started. So we're starting off with electromagnetic induction and flux. Okay, this video is going to be quite short. It's just a very short introduction to what we're going to be talking about here and how this principle, how this idea was first discovered. So, have a look at this diagram. Basically what we've got is some kind of battery, okay, a DC voltage source, that's very important. We've coiled a wire that's attached to this battery around an iron ring. Okay, so this battery is coiled around the left-hand side of this ring. And on the other side, we've got another coil of wire, not connected to the first one. And this is coiled around and connected to a ammeter, galvanometer, whatever you want to use, a multimeter of some kind. And famous scientist Michael Faraday, he was investigating how we could probably produce electricity using magnetic fields, okay? Because it was already kind of known at the time that currents produce magnetic fields, okay, as demonstrated by Hans Christian Ørsted. That was in the previous area of study. Okay, so currents generate their own magnetic fields. So Faraday thought, well, if currents can generate their own magnetic fields, then maybe we can flip it the other way around and use magnetic fields to create current. Okay, and this is what he set up. Okay, so the goal was that when he switches the battery on, that current flows in the left-hand coil. The current will produce a magnetic field. That magnetic field will propagate throughout this iron ring, and that magnetic field would in turn somehow create a current in this secondary coil. Okay, and that current could be measured using some kind of measuring device. Okay, that's basically what I just said. Now, here's the thing. Faraday didn't find any current. Okay, at least not when he kept this battery switched on. Okay. However, what he did notice was that at the moment that he switched the battery on and off, so he closed and opened this switch, at the moment of the closing and opening of the switch, the ammeter on the other side jumped, but then it quickly returned to 0, okay, after the battery was kept on. So just the battery being on by itself isn't the thing that is producing this current, okay, because once we leave the battery on, you see that this ammeter on the other side returns back to 0, even though the battery's on over on the left. However, when the battery is switched on, okay, at the moment of switching the battery on, the ammeter does a little jump. So it flicks off to one side, okay, but then very quickly returns back to 0. Interestingly also is that when you turn the battery off, okay, at the moment that you switch the battery off, the galvanometer or the ammeter quickly flicks in the other direction, but then returns back to 0. Okay, so something's going on at the moment that you're switching the battery on and off. okay? And that was this discovery, okay? What we've discovered here is electromagnetic induction. Something's happening with the magnet or the magnetic field that's being produced when we switch the current on and off, okay? Now, it's not that the magnetic field itself generates a current in this secondary coil. Okay, notice we're always talking about when the switch is being opened and closed, when the current is being switched on and off. Okay, so let's think about what happens in stages about this little experiment that we've got here. Okay, so initially the switch is off. Let's just say initially the switch is off. Okay, so the current through the wire, what is going on there? Current through the wire is 0. Okay, so that's when the battery is switched off. When you switch the battery on, it produces some current, okay, and that current's going to go this way. Now, when you have a current going through a coil of wire, okay, as we saw in the last area of study, the current will produce a magnetic field through that coil, okay? So in terms of the current going through this coil on the left-hand side, which we'll call the primary coil, let's use a grip rule to determine which direction the magnetic field is going to be through this loop, okay, and it's going to be propagating throughout this ring. So if you imagine the current going up the back and down the front of this wire, up the back and down the front, okay, get your left hand, stick it out in front of you, okay, and imagine that the current is going up the back and down the front. So curl your fingers sort of around towards your face, going up the back, down the front. And what you should see if you're using your right hand is that the north side of the magnetic field that would be produced is going to be on the right. Okay, now if you just rotate that picture a little bit, that's going to mean that the magnetic field that's being produced through this loop here, it's basically a solenoid, is pointing this way. Okay, so this would be the north side of the magnet, electromagnet. This would be the south side. Okay, so the magnetic field's going in an anti-clockwise direction around this loop. Okay, the magnetic field goes through the loop all the way around and enters through the other side. Okay, so that's what happens when you switch the current on. All right, now think about the moment before you switch it on and the moment after you switch it on. Okay, the moment before you switch it on, there is no magnetic field in the loop because there's no current in this primary coil. How can there be a magnetic field? All right. However, when you switch the current on, then the current in the primary coil produces this magnetic field that goes anti-clockwise around the loop. So initially there was no magnetic field, then there was. Okay. And what we can describe this as is a change in the magnetic field strength through this iron loop, this iron ring. Okay, so there is a change in the magnetic field strength. Now, that is the thing that causes a current to be what we call induced in this secondary coil. It's not the magnetic field itself, it's the change in the magnetic field, okay? And that's why after you leave the battery on, that you don't see any current being produced in this secondary coil, okay? The reason for that being is once you switch the battery on, the magnetic field is going to be a constant strength throughout this iron ring. It's not going to be changing, okay? It's going to be a constant value. And so, because there is no change in the magnetic field, there is no induced current in the secondary loop, in the secondary coil. However, when you switch the battery off, then what happens is you go from having a magnetic field to not having a magnetic field. So there is a change in a magnetic field. And so if you were to make the assumption that a change in magnetic field induces a current in this secondary loop, then that's in fact what you would see, and it is in fact what we do see. That's what he saw when he did this experiment. So switching the battery on and off, changing the magnetic field through this iron ring, is the thing that causes a current to be induced in this secondary coil. Okay? So what have we discovered? We've discovered electromagnetic induction. Okay, and this is the idea that a change in a magnetic field is what causes a small jump in current to be detected. And we're talking about current in the secondary loop. Okay? So it's not just the magnetic field's presence. Okay? The presence of a magnetic field is not enough to induce a current. It has to be changing. That's the really important thing that we're trying to get through in this video. Okay? A change in a magnetic field is what causes a current to be induced. Okay? Now, we're using kind of specific terminology throughout this area of study. Most of the time we're going to be using the phrase EMF. EMF stands for electromotive force, but this is really just another name for voltage or potential difference, okay? So it's just the terminology we're using in this area of study. We're going to give EMF the symbol, this symbol here, which is an epsilon or a variant of the epsilon symbol. When you see that, that just means induced current, or induced voltage. Okay, so the induced voltage that's produced by changing magnetic field. Okay, so that's the introduction to what we're going to be looking at here. Okay, we're going to be looking at how we can cause a current to be induced, or rather a EMF to be induced by somehow changing the magnetic field around a conductor of some kind. Okay. That's the principle that we'll be looking at through this entire section. Okay, another thing that we can look at also here, it's kind of a variation of what was going on before. If you somehow just attach a copper wire to an ammeter, such as in this diagram here, okay, the copper wire doesn't have any external voltage source, okay, it simply just goes from one end of the ammeter around to the other side. Okay, and what you could do is if you had some really strong magnets, you could put them close together like this to produce a magnetic field in between them. And what you can do is you can drag this copper wire through this magnetic field region. Okay, and what you would see is a current being detected by the ammeter. Okay, so if you drag a loop of wire like this through a magnetic field, you would in fact see that there is a current being induced in this wire. Okay. Interestingly enough, so once we drag it through, yes, you see a current being produced because you are changing the magnetic field around the wire, because you're dragging it from one position to another position through the magnetic field like that. If you stop dragging it and you just leave the wire in the magnetic field, the current will stop being induced. Okay, because you're not changing the magnetic field around the wire anymore, you're just leaving it in the magnetic field. Okay, and if you drag it in the opposite direction through the magnetic field in this third picture, the current gets induced in the other way. So initially it was going anti-clockwise through this copper loop, and now if you drag it the other way, it goes clockwise. Okay, so that's interesting. The direction or the way in which the magnetic field changes somehow determines the direction of the current. And one last thing also is that if you drag this wire parallel to the magnetic field, okay, because we're considering the region right in between these two magnets to be uniform, if you drag this wire parallel to the magnetic field lines, the strength of the magnetic field is not changing, because as we know, in between two magnetic objects such as these, the field in between is pretty much uniform. Whereas if you drag it from top to bottom or from bottom to top, it's sort of weaker at the edges than it is in the middle. Okay, so that's why you do get a change in magnetic field. But if you just drag it straight through like this, okay, straight through, why is that happening? Straight through from one side to the other, parallel to the field lines, you won't detect any current because there is no change in the magnetic field when you drag the wire through it in that way. Okay, so some things to think about. Okay, we've seen that somehow changing a magnetic field around a wire or a conductor of some kind induces a current inside that conductor. Okay, there's something going on with the electrons inside due to the changing of the magnetic field. Okay, so that's our introduction. We're not going to go into too much more depth here. Okay, here's our summary. So we've got a change in magnetic field being applied to the region of a conductor causes the conductor to experience a potential difference, voltage, EMF, whatever you want to call it. Okay, and in turn, if that is a closed circuit, if that conductor forms a closed circuit, you get a current. This generation principle is called electromagnetic induction, the idea that changing the magnetic field strength around a conductor induces an EMF. And what you can do to do this is you can move a conductor through a magnetic field, such as we saw in the last slide, or you can vary the strength of the field around the conductor by leaving the conductor stationary. Okay, so long as the field is changing around the region of the conductor in some way, you will get an EMF. Okay, so that's it for this video. We'll stop there, and I will see you next time.